Hey everyone, welcome to section 3, electrons in the atom. This video is for honors chemistry, so if you are in the wrong video, then make sure you switch to the other video. We've talked a lot about the protons and the neutrons so far, and now we're going to spend some time talking about the electrons that are in the atom. We've already said we know electrons are in energy levels. We know that they're found in the electron cloud. And as you move out from the center, the energy levels go up from n equals 1 to n equals 7. Higher energy on the further out, lower energy closer in. The ones that are going to be found in the furthest out energy level are going to be considered the valence electrons. So even though we know that the Bohr model of the atom is not considered to be the correct model any longer, we do know that energy levels are located at set distances. You guys saw when we looked at the quantum mechanical model that there are areas or zones where you would find the electrons at the first energy level, at the second energy level, etc. Those energy levels, as mentioned, are designated as n equals 1, n equals 2, n equals 3. And every energy level can contain a specific number of electrons. It is very possible that you had to memorize these in middle school, and you will probably pick it up again. But the first energy level holds the fewest number of electrons. It only holds 2, and that's the one closest to the nucleus. It also has the fewest number of sublevels. It only has an S sublevel. And we'll get to the sublevels in the next section. The second energy level all the way up to the 7th, they can hold a lot more. They have higher energy, and they have more sublevels, therefore they hold more electrons. The normal traditional location where the electron is, if it is not struck with electricity or energy or light or heat, is going to be referred to as its ground state. If it absorbs energy and moves to an energy level that's higher than the current level it's at, it will jump up to another energy level. That is referred to as its excited state. Okay. Now, the problem is that just like with gravity, if you jump up in the air on a trampoline, you don't necessarily stay there. That would be rather terrifying if you did, if you like froze in the air and you couldn't figure out how to fall back down. The same thing happens with the electrons. They can't stay at that high energy level. They fall back down. And as we mentioned before, I started mentioning a little bit with the quantum stuff. You know, this is official. Let's say energy level 1 correlates with 100 units of energy, and energy level 2 correlates with 200 units of energy. If we have an electron that absorbs 100 units of energy, and it jumps up to the second energy level, it can't necessarily stay there. That energy level is already occupied and perhaps already full, so it's not able to stay there for that full amount of time. So it's going to have to fall back to its original energy level, but numbers don't lie. It has to give off that energy that it had. The amount of energy it gives off is correlative with a specific type of light or radiation that comes out of the atom when that happens. If it's a low energy, it's going to give off light such as reds or yellows, colors of visible light, even all the way down to radio waves and microwaves, etc. If it is a high energy, it could release gamma radiation, it could release X-rays, it could release very, very high radiation, high energy radiation. So light, when it is released in packets of energy called photons, and this is just a joke, so just enjoy that. All of the energy that we know that is basically forms of light are all part of the electromagnetic spectrum. The spectrum has the lowest energy waves or radio waves all the way up to the highest, which would be gamma. Okay? The light that we actually can see is found right here in the middle. Those are the ones that we are capable of seeing. Other animals can actually see higher than that, can see up into infrared, or excuse me, down into infrared, up into ultraviolet, etc. We just don't happen to. The lowest energy waves also have the longest wavelength and the longest frequency. Longest frequency. So, if a wave is very large and flowy, like these down here at the bottom with microwaves and radio waves, then they are very low frequency. They're not occurring very fast, essentially. The energy of the wave is relatively low, and the wavelength is very large. As you move up to the gamma end of the spectrum, wavelength becomes very short, energy is very high, and frequency is also very high. It'll have a very high frequency. Really quick, in case any of those words are freaking you out, when we're looking at a wave, we look at their crest and their trough, and general electromagnetic waves are these waves like this, these transverse waves that go up and down. So when we're measuring wavelength, we're going to measure from the same point on one wave to the same point on the next wave. So wavelength is basically how far apart the waves are. Frequency refers to basically how fast the waves are occurring. So if you have a high frequency, it means that you have a lot of waves or a lot of crests passing over a certain point at a very high rate. So that means that it is generally going to be very high energy if you have a high frequency. If you have a low frequency, it would be very low energy, meaning the waves are moving pretty slow, so they're not going to be passing over that point very fast. We're already 9 slides in, and we haven't talked about math. I have a solution for that. Get it? Solution because of like calculation? All right, whatever. Wavelength is calculated by using speed of light and the frequency of a wave. So when you're calculating wavelength, essentially we use this box over here. Okay? And so the general idea, of course, with any of these little triangles is that the space between the upper and lower area is essentially a division, and the space between the two at the bottom is multiplication. So if I need to solve for C, then I would multiply wavelength times V. If I need to solve for V, then I would take speed of light divided by wavelength. If I need to solve for wavelength, I would take speed of light divided by frequency. So that's how we redesign the formula to solve for the correct wavelength, or solve for whatever we're trying to solve for. C is 2.9979 times 10 to the 8th meters per second. You do not need to memorize that. It'll be on your formula sheet. You just need to know that C is speed of light and that you need to plug in a number. Okay. Notice it is in meters. So speed of light needs to be in meters per second, and it will be given to you in that way because that is a constant value. Okay. Wavelength also in that case needs to be in meters. Okay. A lot of times you're going to get a wavelength in nanometers, and you'll just need to make sure that you convert it to meters, okay? And there's 1 billion nanometers in a meter, so 10 to the 9th. So you'll have to brush up on that conversion. Remember that, memorize the nano to meter conversion. And then frequency is generally going to be in hertz, although you could have kilohertz and you could have megahertz. So go back to our fundamentals of chemistry unit, back to that section 1 PowerPoint, and restudy the conversion factors for nano, kilo, and mega, okay? Okay, so looking at the first practice problem here, it's asking for wavelength of light emitted from an atom in nanometers if the frequency of the radiation is 5 times 10 to the 12th hertz. All right, well, what I see here is I right off the bat see wavelength. I right off the bat see frequency, and so I know that I am, in this particular case, I am solving for wavelength. So what that means is that when I look for my formula, it's going to have wavelength equals C over a curve V. Okay, curve V is frequency. So that's what I'm going to do my calculation for. The speed of light in a vacuum is C. The frequency is 5 times 10 to the 12th hertz. Plug that in, calculate, I get 0.000599 meters. Question asks for nanometers, so I need to do the conversion, multiply it by 1 times 10 to the 9th, which is a billion basically, and I get a value of 60,000 nanometers. Once I calculate with sig figs, of course. When I look back at my problem, I had a value of 5 times 10 to the 12th. 5 is 1 sig fig, so I only had 1 sig fig in my final answer. So around 60,000 nanometers is the wavelength of light at that frequency. In the second calculation, it says the wavelength of green light is 522 nanometers. It does say there convert to meters. Just as a reminder, you need to make sure that your wavelengths, unless you are asked to convert them to nanometers at the end, your wavelengths need to be in meters. Okay. This one's asking for frequency. So what that means is that I'm solving for my fancy V, so I'm going to have C over lambda, or frequency. Okay. So in this particular case, I need to go ahead and convert that by dividing by 1 times 10 to the 9th, because that is how I convert nanometers back to meters. And so that gives me 5.22 times 10 to the negative 7th meters. And then when I reconfigure that formula, because I'm going to end up essentially multiplying both sides by V, and then dividing both sides by 5.22 times 10 to the negative 7th. So I end up, of course, getting C over lambda. And in that particular case, when I solve for frequency, I get 5.74 times 10 to the 14th at 3 sig figs. As mentioned, when light is released, it is released in packets of energy called photons. What we also are going to be doing in this unit is calculating how much energy is in that particular photon. And it shouldn't surprise you that, that energy of the photon is really based on the calculation involving frequency or wavelength, because both of those things are affected by the energy. If you have a high energy wave, it shortens the wavelength, it increases the frequency. So when you're calculating, you're going to use one of these two formulas that's down in the bottom. E equals HV or E equals HC over lambda, okay, which is wavelength. So the H is something new, and H is what we call Planck's constant. So Planck's constant is 6.626 times 10 to the negative 34th. Wow, that's a really small number. Joules per second. Joule seconds. So it's not showing up here, but it should just be a dot because it should basically be joule seconds. Okay, so joules times seconds. The unit there, again, you're going to be given Planck's constant on your formula sheet. I don't expect you to memorize Planck's constant. I just want you to be able to use it, okay? So when you're calculating energy, energy is capital E. Planck's constant is H, frequency in the left-hand formula. So if you only have frequency and you're asked to solve for energy, you're going to multiply Planck's constant times the frequency. If you have wavelength and you're asked to solve for energy of the photon, you need Planck's constant as well as the speed of light with the wavelength. Okay, so first question is asking us to calculate the energy of a photon of blue light with the wavelength of 450 nanometers. Of course, start by converting that to meters. So I'm going to, in this particular case, divide it by 1 times 10 to the 9th, which gives me 4.5 times 10 to the negative 7th meters. And in order to calculate this, I need to use Planck's constant times the speed of light divided by the wavelength, and that ultimately will give me 4.4 times 10 to the negative 19th joules. Joules is the unit of energy, is the unit of energy that we're going to be using, and that is the energy of that particular photon of light. In the next question, what is the energy of a photon corresponding to radio waves with a frequency of 1.255 times 10 to the 6 hertz? Well, I have frequency, so that means I need to use E equals HV. So H is Planck's constant, of course. V is the frequency. When I multiply those two, I get 8.316 times 10 to the negative 28th joules. So there's not much to say about visible light other than that, of course, that's the part of the spectrum we can see. Invisible light, just like with the rest of the spectrum, in this particular image, visible light is located right here in the middle. As you move to the right, you are going down in energy. As you move to the left, you are going up in energy. And energy, wavelength, and frequency are all correlated, okay? So the shorter the wavelength, the higher the frequency, so they have an inverse relationship. And so red being that it has the longest wavelength of the visible light, has the shortest frequency, has the lowest energy of visible light. So purple and blue lights are much higher energy, have a shorter wavelength. Those are going to be the types of things you would see when electrons are falling from very high energy levels down to very low energy levels. You would generally see reds and oranges if they're dropping from low energy levels down to even lower energy levels. Every single shade of light in the entire visible light spectrum corresponds to a specific wavelength. Our eyes are designed to pick up specific wavelengths and translate it to our brain to tell us exactly how to view that particular color. So when I look at something that's bright blue, my mind is picking up, hey, this is a pretty short wavelength, this is a pretty high energy thing. It's not super high, but it is pretty high, so let's convert it into the color that we're going to see, and that's what happens. So really, your brain is just doing conversions all the time. So sorry about it for those of you that hated conversions, but you're just a walking, talking conversion. When electrons are going to emit energy, they emit a color, and the color depends on how much energy is emitted. If it's falling from a really high energy level down to a low, it gives off a high energy wave, shorter wavelength with a high frequency, probably the purples and blues. If it's doing a very small fall, it's going to give off reds and oranges. So here's a great example to show that. In this particular case, we have an electron falling from the third energy level down to the second. Now, it's very likely that this electron may have started at the second energy level, absorbed energy, went up to the third, now it's falling back down. Because it's only dropping one energy level, it's giving off, in this particular case, a red light, meaning that it's going to be a pretty low energy. On the other side, we have one dropping from 4 down to 2. That's giving off green. That's going to be, pretty medium energy. Higher energy than the red light, but not as much as blues and purples. The really cool thing about all this is that every single element has a specific number of protons, and usually a traditional atom would have a specific number of electrons. Well, those electrons are going to behave in certain ways depending on how many electrons there are, depending on how much positive charge the nucleus has pulling in. And so every atom has a signature. Every single element emits a specific pattern of light and color that no other element is going to have. And so that is essentially, if you've ever wondered, how do they even know that, Neptune is made out of primarily nitrogen and methane gases? How do they know that? This is how they know that. They know based on the type of light that those things are reflecting when they are struck with the sun's energy. So we know that Neptune is made of a lot of methane because it reflects certain wavelengths of light that correspond to carbon and hydrogen methane compounds. So that is how we can figure these things out. When you look at this, at the top on the right-hand side here, we have the sun. That gives off a lot because it has a lot of energy going on there. And then we have hydrogen, helium, mercury, and uranium. These, definitely you can tell, the more protons and electrons the atom is going to have, the more different wavelengths of light it's likely going to give off. But these are their fingerprints. These are the signatures for those specific atoms. And we're going to do something with this next time. All right, summarize, and I want you to work through your practice problems, and I will see you guys next time.